Good morning, everybody. Thanks a lot for attending the talk, and also hello to the people on Zoom. Today I will present the results that I obtained in the last 3 years during my PhD here at SPIN-ITN, and also I want to mention that this project was funded by the SPIN-ITN. So the topic of my PhD is detection and characterization of seismic signals using distributed acoustic sensing, also known as DAS. So in the beginning, just a brief overview of the presentation to come. I will motivate my research and give the current state of the art. Then I will introduce the methodologies that we implemented and tested during the thesis. And then I will apply those methodologies to 3 different case studies. The first one is from an urban area, measured here in the city of Grenoble. The second one was measured at the volcanic area at Mount Etna in Sicily. And the last data set is from the Courne-d'Arvy slope instability, which is one of the largest slope instability in the Alps. Finally, I will conclude my results and give some perspective on future research. At its origin, seismology started because of earthquake detection. And in the last 100 years, instruments became much cheaper and also lighter. And for that, seismic networks continuously expanded. And we can see this especially when we look at the number of detections that we had in the last 100 years. They increased ever so more, and this is because we had more seismic stations available, which allowed us to detect smaller and smaller events. And this helps us to study processes in more detail. But also seismicity is much more than just earthquakes. So I give a few examples for the 3 case studies that I analyzed during my PhD work. So first of all, we have a volcano in the bottom left, and volcanoes are very complex physical systems. So there are a lot of processes happening. For example, there's a lot of hydrothermal fluid movement. So we have the gassing at the surface, sometimes explosions and even eruptions. But also there are faults in the subsurface, which can lead to a volcano-tectonic earthquake. And also inside the conduits and magma chambers, we can have processes such as VLP, for example. And all these processes, when they happen, they are quite energetic, and they also radiate seismic energy, which we can thus measure. And in the top, I have a sample toy seismogram, and this shows a VLP event. Then moving to the right bottom, we have a schematic of a landslide. So a landslide can catastrophic failure. This is the worst possible scenario, and this is also very energetic and releases a lot of seismic energy. But also, for example, rock falls, when rocks are falling down the slope, each time they bounce on the subsurface, they act as a seismic source. And finally, in a city, we don't have so many natural events usually, depending on the place where we live, but there's a lot of anthropogenic sources. So for example, cars, when they're driving and they're braking, they continuously radiate surface waves, which can be measured. So during my thesis, I mostly worked with distributed acoustic sensing, and this is a new type of instrument, which was originally developed in the oil and gas industry in the early 2010s. But these days, it's increasingly used for monitoring natural seismicity. And the setup of such a system is actually quite simple. You have a fiber optic cable, which acts as a sensing element, and to this fiber optic cable, we attach a so-called interrogator unit, and this unit sends a laser pulse into the fiber, records backscattered light, and then computes the strain rate every few meters. So the principle how this works is because the glass inside the fiber cable, it's not perfect. There are lots of impurities. These happen during manufacturing or also handling, when there are small gas trapped or when there are small breaks. And at these impurities, when the light pulse that we send in interacts with them, the light is scattered. And this is scattered in all directions, and some of the light also travels back. So this light can be recorded. Now, these location of these scatterers are quite random, so we don't know them, but we expect that each time we send in a light pulse, we should get back the same characteristic spectrum of backscattered energy. And this is for the case where we wouldn't disturb the fiber at all. But now, and this is shown with the delta L, we would elongate or compress the fiber, the locations of these scatterers would change. And the result of this would be that the backscattered energy has a phase shift. And actually this phase shift is proportional to the strain along the fiber. And this is typically done for a gauge length. So we don't have point strain, but we estimate the strain over a certain length. In most dust experiments, this is 10 meters. And we can make such estimations every few meters. And because of this, we can have cables which are over tens of kilometers long, and we have spatial spacing every meters of a measurement. So with a single dust experiment, we can have thousands of dust channels. So each of these sensor points is called a dust channel. And just for comparison, the International Monitoring System has around 200 stations, or the Seismic Japanese network has around 2,000 stations. Just to let you know that these dust experiments, they have a lot of data. And also, I want to say that distributed acoustic sensing, it can be sometimes a bit confusing name because we don't only measure acoustic waves. So there's some effort to call it distributed dynamic strain sensing because actually you're measuring dynamic strain. But in this talk, I will call it dust because it's the most well-known name. So the main advantages of dust is, I would say, one is that we can store the interrogated unit in a safe location. So once we have the fiber in place, we just have to connect the interrogator unit, and this can be done in a room if it's available or quite away from the dangerous area, which is, for example, quite important for the volcano, because once the fiber is there and the volcano is erupting, we wouldn't want to go there to change instrument. But if the cable is running quite long and we can store the interrogated unit in safe locations, it's quite nice. Also, we can leave the cable in place for future measurements, so we can just leave it there. Each time we want to go, we take our interrogator, we connect it, we measure, and we take away the interrogator, and leaving just the cable in place. Meanwhile, if we had a huge nodal area of thousands of stations, each time after measurement campaign, we would have to collect the instruments, read the data, recharge the batteries. And as I mentioned before, we can have quite long cables, so there are already measurements above 100 kilometers, and the spacing of these dust channels can be less than 1 meter. And finally, dust has quite a broad frequency response. So you can measure from 0.1 hertz to a few hundred hertz with high fidelity. But dust has also some limitations. As I told you before, we measure the strain along the cable, but we don't measure it in the other directions. So we only have a one component measurement, while the typical seismometer has the 3 spatial locations in displacement. And in the bottom right, we have a waveform simulation from Hubbard et al. From its vertical source, and we have a cable that's in the X direction. And what we can see is that if the wave is traveling in the X direction, we have a maximum sensitivity, while if the wave is going broadside to the dust, we're actually, it's invisible to us. And this can be quite a limitation. Also, there can be quite some non-trivial waveforms, especially if we take into account that we measure the strain over a gauge length, which is mostly 10 meters. So for example, when the gauge length has a similar magnitude than the wavelength, we will get some distortions. Also, what can be quite problematic is that the ground to cable coupling, it's not always perfect, which means what we record, we cannot always take the absolute amplitudes. And for a lot of seismological applications, we need the absolute amplitudes. This cannot always be done with dust, especially for urban applications, because there the fiber most often is just laying into the concrete and is badly coupled to the ground. Also, dust on the single channels has quite a low signal to noise ratio compared, for example, to broadband seismometers. And finally, we have lots of measurements, which is great, but this also means that we have huge data sets which need to be stored, which need to be processed. And also sharing can be quite difficult of these data sets. So I worked mainly on signal detection, and I first want to say currently there's not really established standard workflow. So most projects, what they do is they develop their custom methods for their target application. And there are quite a few challenges with that. We have these large amount of data. Often for the first dust experiments, we don't really know what kind of signals we expect. And finally, the data quality is often not great. So we try a new application on dust to see if we can tackle those challenges by implementing and applying coherence-based methods. And especially we use 2 methods, which is the array covariance matrix analysis and also template matching. And both of these methods take advantage of the array nature of DAS and are not so sensitive to individual noisy channels. So now I will go a bit more detail about the methods. First of all, I mentioned the signal coherence, which is a measure of the similarity between two time series. And this is a bit the core concept also for the other methods. Here's a formula, and we calculate the cross-spectral density over m snapshots and divide this by the auto-spectral density, also average over m snapshots. And because we have this average, it means that the phase of the two signals should stay constant, because otherwise we have destructive interference. And because we normalize it, this is a normalized covariance, and it's bounded the magnitude between 0 and 1. And also because this comes up later, first we have those snapshot windows for which we calculate the cross and auto-spectral densities, and then we average m of them. So in the end, we also have the final signal coherence estimate for a longer time window. And here's just two toy examples to exemplify this. I have two signals on the left side. The first one, like both of them, are made up of sinusoids with constant phase. The blue one has 3 components at 5, 15, and 25 Hertz, while the orange one just has one at 5 and 25 Hertz. And when we compute the coherence between them, we can see that it nicely picks up that both of these signals have similar coherent signals for these two frequency components. On the right side, however, I varied the phase randomly every snapshot, every 500 milliseconds. And because of this, in the final coherence estimate, we don't see those peaks. And this is just to show you that the most important thing is that for signals that you want to record, the most important thing is that the phase between the different sensors stays stable over some certain time. Next, I want to talk about the array covariance matrix. And this was first developed for seismic arrays by Sedou et al. In 2016. So here's an example from a few nodal data from the Etna volcano. I highlighted 2 windows. One of them includes quite a strong signal, while the other one includes noise. And in the first step, we calculate the covariance matrix, or in this case, I computed the coherence matrix. And as we can see, is that almost all across the matrix. So each entry of this matrix is the signal coherence between 2 different channels for all channel pairs. We see that we have mostly elevated coherences. On the other hand, for the noise, we have rather low values. Now, in the next step of this method, you compute the eigendecomposition of those matrices, and we can see that for the matrix, like including the signal, we have one eigenvalue which is much stronger than the other ones. Meanwhile, for the noise example, the distribution of the eigenvalues is rather flat. Now, we can estimate if we have one eigenvalue or few that are dominating the other, or if it's quite rather broad. And this is most often done by this spectral width estimate. I gave the formula below. And we can do this process to compute this coherence matrix at each time window and for different frequencies. And by that, we can populate a so-called array spectrogram. So in this method, the first way to detect would be actually to take the spectral width or this final spectrogram and do detection on that. But also for each of those eigenvalues, there are corresponding eigenvectors. Mostly the most interesting is the one relating to the strongest eigenvalue. And we can also use this and do some kind of detection, either by clustering those eigenvectors or by using an eigenvector of a known event as a matched filter. And this was also first tested by Sylvester et al. In 2018 for seismic networks. The next method I want to talk about is template matching. For template matching, we select a template event, and this template event is scanned through the whole data, and we try to find windows which have a high similarity to this template. So at each time step, we take the window data, we compute the cross correlation with the template, and if it's above a certain threshold, we raise a new detection. So here again is this toy waveform in the beginning, and now we scan the waveform with our template. So in the first case, these are 2 different events. So we have a low cross correlation value and no detection. Meanwhile, if we have a window which includes a signal that is similar, this will lead to a high cross correlation, and we would raise a detection. And again, if the window just contains no signal or noise, and we do the cross correlation, it would be low, and we detect not a new signal. And this method can be quite powerful because even if we have a very small signal in our dataset that's hidden in the noise, this method can pick it up. And so it's often used to as a final step after we have a good initial catalog to complete it. But also to note in the first part, like in the very first window, we had a signal, but it was a different signal, so we wouldn't be able to detect it. So this shows that we need good initial templates which represent all the events in the data, so that this method is very effective. So now I'm moving on to the first project that I worked off, and this was a dust recording on dark fiber here in the city of Grenoble, and we used wave field decomposition to understand this data or make some sense of it. And this was done in collaboration with Bastien Zingriba and Olivier Couton. So here's an overview of this data set. First of all, you have the outline of the cable, which is mostly running along streets. And on the right of it, you can see some typical data. And most of these strong signals are due to traffic. It's either car signals or around channel 200. These are trams. The fiber has a length of 13.6 kilometers on the map. I will talk about this in a second. And the measurement was for a little bit over 10 days during 16 to 27 of December 2020. And for those who remember, this was during the COVID restrictions, so there was not a clear lockdown, but there were some restrictions in place. And this data set had a size of about 1.3 terabyte, which for some might sound large, but also for a dust data set, it's not so large. A problem was that we got the map of the fiber from the telecommunication company, and actually there was a gap between what the dust interrogator measured and the location on the map. And this can have a few reasons. For example, if the cable is not completely lying straight in the conduit, but maybe it has some turns, and also it can have some loops and manholes, which would effectively gain distance in the fiber, but not in the physical location on the map. So this can be quite problematic because this means that we're quite far away from the interrogator. When we see a signal, we don't actually know exactly what location it is, and therefore we need to relocate the signals. And we did this by taking characteristic points in the map and also characteristic signals in the data and matching them. So for example, the yellow arrows on the bottom right, they show a signal, and this is of a bus. And we can see that the bus is driving, when it's stopping, and it continues driving. And at the moment where it's stopping, these are the points in the map where are the bus stations. So this we can use, for example, to relocate the data. So here's an example. And if we filter it at low frequency, we actually don't see the seismic waves, but we see the static strain. And we can even see that while the bus is stopping, we have a continuous static strain. But also, for example, we have intersections in the road or roundabouts. So this is a car driving across the cable at an intersection. And we can take all those points to get a confident estimations of the cable location. In the next step, we computed coherence matrices, like I showed you before, for all 20-minute windows. So we took windows of 20 minutes, took the whole data set and computed coherence matrices, and then we averaged them in four frequency bands. In the 1 to 5 hertz, in 5 to 10 hertz, in 10 to 20 hertz, and from 20 to 40 hertz. And here's an example showing the averages from 1 to 5 hertz for three different times. So in the middle of the night, also when the curfew was in place, we actually see no strong signals at all. And also the coherence matrix, which is shown in the top of the map, is quite dark. Then in the early morning hours, we start to see some traffic coming into Grenoble. And we can also see that then in the coherence matrix, we see some elevated coherence at the diagonal corresponding to those signals. And finally, we have more and more signals when we get to rush hour. So our goal was to understand these signals and their behavior in a quite complex and noisy data set. And we did this by using non-negative matrix factorization. We took all the matrices for all time windows, and then we used non-negative matrix factorization to find repeating patterns in those matrices. And the main result of this analysis is shown in the next slide. So here I show the first 5 components of this decomposition. And the matrix in the middle, it shows the feature matrix. So this is a region of elevated coherence that is appearing repeatedly in the data. And then on the left side of it, you can see the activation coefficient for each time window. And this is quite nice because it shows us that if we have some sources which cause a elevated coherence in some regions, we actually know exactly at what times it is occurring. And also the weighted histograms, which are shown on the right, show that most of these signals are currently related to anthropogenic activity, which is not quite surprising since we measure data along roads. Quite interesting is the fifth component that I show here, because this one doesn't show like a clearly localized region, but it mostly shows many regions along the cable. So this is more or less the coherence of the whole city of activity. And we can see that clearly this follows the city activity, and it's weaker on Sunday and also on the last Friday, which happens to be Christmas Day. And also we can see that the spectrogram that it's bounded perfectly between 6 and 20 o'clock, and this is the curfew imposed by the French government. So we see in those data the working hours and the COVID curfew. And also, for example, on the last Friday, from Thursday to Friday, we see that it's actually, the activity is going longer than midnight. And this was because it was special Christmas Day, so the government allowed exemptions for the curfew. But also there's much more signals in the data. So for example, now I show feature 1, and this is a repetitive impulsive event. And also we can see for the time series is happening during the day. Sometimes we have a break at the lunch hour where the activity is going down, and on the weekends and some other days, maybe it's already Christmas holidays, it's not working. And these are repetitive transient events. So these are seismic waves traveling there. And the location of the apex of the waveform is quite close to an electronics factory, which could be a potential source. And we can utilize those signals. So I give a proof of concept for this by computing dispersion curves for a very short time window, in this case 30 seconds of data. And we do this, it's quite neat. We can just take the time series, we select a window where we know that the source is active, and then for that time window, we can compute a dispersion curve. In this method, I use the lens stack method, and we have quite a low time resolution. So I looked a bit in the literature, and there are a few other studies which show dispersion curves for very short time windows. For example, this is one computed by Yuan et al. For a single car traveling, and what they see for cars is that typically they have it's quite stable at higher frequencies, but at low frequencies it's quite challenging. So our signal is mostly located between 2 and 6 Hz. So this could give complementary information, especially if we want to constrain deeper layers. So to conclude project 1, we developed a new method, and this is able to detect regions with coherent energy and also the temporal activation of those regions. The confirmed sources can be used directly for monitoring the subsurface structure. And we can, with this method, track city dynamics, for example, the activity of the sources, but also with potential imaging from dispersion curves to some seismic hazard assessment. And this could be integrated into smart cities. So now I'm moving on to the next project, which was about detecting seismovolcanic events at Mount Etna. And this was done in collaboration with Philippe Jousset. The data that we analyzed was from the Line network, and this is publicly available. It's for 16 days in August of 2018, and the cable is about approximately 1.5 kilometers long with a 2-meter channel spacing. On the DEM on the left side, you can see the 5 main craters of Etna volcano, and the cable is located approximately 3 kilometers away. And also we have 15 geophones that are placed or co-located with a fiber, which you can use for comparison. And in the bottom, you can see 1 hour of data, just to show you that there are really lots of events in this data. And there's an array spectrogram, which also reflects that there are many signals in the data. To focus more on the array spectrograms, here are a few examples. Again, a reminder that low values indicate a dominant source. So low values mean that we have a strong signal. In the bottom left, you can see typical degassing activity, and at the end, some anthropogenic signals from cars driving. In the top right, we have a volcanic explosion with a broad frequency response. And in the bottom right, we have a volcanotectonic earthquake, which more lower dominant frequencies. And what is quite nice is that this method, without any prior assumptions about the wave field, that means like the source characteristics or the velocity structure, is able to or is quite sensitive to all these sources. But this comes with a computational cost, and this is especially important for DAS because this computational cost doesn't square very nicely with the number of stations. If we plot it in a log-log plot, the computation time versus the number of stations, we get a straight line. It's almost a quadratic cost. And this is because at each frequency and each time window, we do an eigendecomposition of a coherence matrix, and this matrix scales with the number of stations. Which means that if we, for example, for DAS, we have 1,000 stations instead of 10, means the computation time would be 10,000 times higher. And this asks the questions, do we really need all the DAS data? Because we sample the wave field every 2 meters. This is a super high sampling. Maybe we can do with 10 meters or 20. So we set out to test this. And first, we tried to look at some theoretical results from other works and do a comparison. And for this, we analyzed eigenvalue distribution, so the eigenvalue decomposition of those coherence matrices for a uniform linear subsection of the cable. So there's a sketch on the left, and all subsections we took are centered across 320 channel location. In the first case, we kept the number of stations constant so that we can compare the different windows because they have the same number of eigenvalues. And we varied just the spacing between the channels from 2 meters to 8 meters. And then on the right side, there are 9 matrices. From top to bottom, you see the increase of the station spacing from 2 meters to 8 meters. And from left to right, we increased the frequency, which decreases the wavelength of the signal. And as we can see, because we have the same number of stations, actually with the 8 meters, we have the largest aperture of our subsections. And what we can see that by increasing the station spacing and by increasing the frequency, both of them would increase the spectral width. And also there's this beta value, which is the ratio between the station spacing and the wavelength. And what we can see quite interestingly is that if they stay more or less the same, then also the width and the shape of the eigenvalue distribution is quite similar. And this is consistent with theoretical expectations from Gersoft et al. And they also showed this for ocean acoustic measurement. But this is actually not the kind of downsampling what we're doing. And so in the next case, I look at true downsampling. This is we keep the aperture of the array constant, but we change the number of stations by just taking every second or every fourth station. And what's quite interesting then is that we see here that for each column, the spectral width estimate, it stays more or less the same, which means even if we take less stations, we get the same result, which means we can safely downsample. But actually, only in the bottom right, we can see that in this case, it doesn't work. The estimate of the spectral width is quite off. And also we can see that the beta value in this case, it's larger than 1 divided by 2. So we have this critical condition, which is the Nyquist theorem in space. We cannot violate this. And this is also known from beamforming. So actually, not only the beta value is important, but the most important is the aperture that controls the spectral width estimate. And we also tested template matching. And for this, we can also see that we can downsample quite safely to a certain degree without sacrificing detection accuracy. So here's the graph. It shows you the downsampling factor, or on the top, the inverse is the number of sensors. And we can see that even up to a downsampling factor of 6, we still get the same number of detection. This is for degassing event. And then we start to drop off. And I want to mention that not only a reason could be this Nyquist theorem, but also for DAS especially, the gauge length, it acts as a low-pass filter, because if we have a station spacing every 2 meters, but our gauge length is 10 meters, it means that neighboring channels actually share a lot of information and are not completely independent from each other. So this also plays a role. And next, we did a comparison between the DAS for the same template and the geophones. And we can see that in the bottom left, I show for 2 hours, the shape of the cross correlation, and they are quite similar, except that the DAS has a higher sensitivity. And this is because it has more channels, but also the reason is that it has a broader frequency response. So on the table, it's just to look up that we, for this time section with those templates, we detected 50% more events for the DAS. And also we can use template matching to study the dynamics. So in this case, I showed 24 hours of the geophone data because unfortunately the DAS data, most often at night, it was not running because it wasn't refueled. And at the top, we have the cross correlation for one template from a degassing event. And actually it has been also very active for the last few days. And then at one point, it completely ceases in activity. In the middle row, we have the time series of an explosion. And we see that it starts at a certain moment, and this more or less is at the same time when the degassing stops. So this indicates that there could be a correlation that the degassing is stopping and those explosions are happening. But also we can see that for different degassing events, it's continuously happening even after the explosions are happening. So this means we could have, for example, some different dynamics that maybe the degassing one template and the explosions, they're coming from the same crater or somehow connected, while the other degassing event is not. And also here's a result from a different study from Zuccarello et al. In 2022, and they looked at the direction of the wave field from an array. And what they could see is that before a paroxysmic event, when the Strombolian explosion started, all of a sudden the direction of the wave field was quite constant below a certain crater. So maybe we see something similar, but what could be quite nice about template matching is that we're not only sensitive to the strongest event, but even when the explosions are happening, we're still sensitive to these very weak degassing. So to conclude project 2, I showed you the examples of the array spectrograms, and they are quite rich show quite rich details for many transient event types. Then we investigated downsampling criteria for DAS data, and especially that this ratio of the station spacing to the wavelength is the most important, but also that the gauge length could play a role. And finally, template matching allows us to detect many events and many weak events, and this is quite powerful for DAS, but it is not so often applied yet. And the reason for this is that we need an initial catalog and good templates. So for example, we could do a combination that we first use the array covariance matrix to get an initial catalog, and then use the template matching to complete this catalog. So now I will move on to the last project, which was about detecting, and this time we also clustered events that we recorded at the Kohn-Davy slope instability in Zittron, Switzerland. And this work was done in collaboration with Gilles Kiers and Cedric Schmelzbach. The Kohn-Davy slope instability, it's one of the largest slope instabilities in the Alps, but it moves quite slow. Actually, we don't call it a landslide but a slope instability because it has a toppling effect, but this is just a definition, and it moves with a few millimeters per month, so not very fast. In the bottom left, we can see a graph showing the velocity over time for 1 year, and we can see that most of the time it's quite stable, but in late spring it starts to accelerate quite significantly, and this is because we have infiltration of meltwater. Just here to show you an example, on the top left of this picture, we have the stable area of the mountain, and on the right side, the unstable area. So this is about 10 meters. So this has been the accumulation of this millimeters per month for many tens of years. In the bottom right, you can see the location of the cable. The black cable is a dark fiber, which was installed by the ski resort. So all on the right side of the plot, this is a large ski resort, which I will also talk about in detail. And we segmented the cable into different sections. And this I will explain in the next slide. So for this project, we utilized the sub-array approach. And this means we didn't compute the array spectrogram for the whole cable, but instead we did it for different subsections of the cable, which are marked here in the different colors on the map. And there's a few reasons for this. First of all, since each of those sub-arrays is quite small, the computation of those array matrices is super efficient because they are much smaller. Then also, because we have less time for a wave to travel through these sub-arrays, we can reduce the time resolution. For example, for these, we took an average window of 10 seconds, which is quite small for this method. And finally, sometimes we have small events which are just visible on 1 or 2 sections. And these are then a bit highlighted if we look at sub-arrays instead of the whole array. And we also implemented a denoising or developed a denoising based on independent component analysis. And this helped us to clean this assemble of those individual array spectrograms and then do a detection. But I will show why this was necessary now, because as I mentioned, this area is a ski resort. So during winter, when the ski lifts are running, there's a lot of mechanical noise from the ski lifts. And so the original sub-array spectrograms are shown on the left side. And we can see that starting from 8 o'clock Swiss time, we have very strong noise, especially on section 1 and section 2, which are closest to the lifts. And actually, it would be very hard to do detection directly there, because a lot of the events of interest are Mars. But also, we would just detect a lot of ski lift noise. So for this, we implemented this denoising, and it works super well, I must say, surprisingly. So we are able to isolate those signal of interest going from A to B. And also, for example, at around 7:30, we see that we have an event which is masked by the ski lift, but after the denoising, we can see it quite cleanly. And again, for example, on section 3 on the right side, we see that we have some events which are only visible on section 3, and this is highlighted by using the sub-array approach. In the next step, we applied this detection to the whole data set, and we had about 7,000 detections. But we had a lot of different sources. So just analyzing those 7,000 events is quite challenging. So in the next step, we tried to group them into different clusters by a clustering algorithm. So I have here a toy example where I took just 16 different events. And to illustrate this approach. So in A, we have 2 events, and from the waveforms, we can already see, okay, these are quite similar. Then we compute the array covariance matrix, and we extract the first eigenvector. In B, I plot the first eigenvector for both these events. In blue is the magnitude, and in red is the phase. And the method is quite sensitive to the phase. For example, we can estimate the similarity between those phases using the cosine distance. And we do this at each subsection and at each frequency. So we end up with many similarity values. And then we take all those values and we compute a final similarity. And from that, we construct a final distance matrix, which is shown as C. And this can be taken directly as input for a hierarchical clustering algorithm. And so we can see in A, we had events 3 and 8. And in D, 3 and 8, they both end up in the red subcluster. And for example, this red subcluster is different from the purple one, which is all the one on the right. And this one includes only earthquakes. So to sum up this method, as an input, we take the catalog of all detected events. And at the output, we get clusters. And in these clusters are similar waveforms. So we applied this to the whole data set of these 7,000 events. And what we ended up with are 6 metaclusters and 30 subclusters. And I will talk a bit now about the metaclusters. Especially, we have some events like regional earthquakes, but also common mode noise, which is a typical kind of noise in DAS. Then on the bottom row, we have explosions, which are quite characteristic because they have an air wave. But also we see signals which are related to natural seismicity, which is the shoulder center, the shoulder west, and the shoulder east. And also we have the histograms again on the right, so we can see that some waveforms, for example, the explosions, they are done by the ski resort to trigger avalanches. For safety, they usually do this in the morning before the ski slopes open. So we see that all these explosions, they happen in the morning at 5 to 7. And also, if we look at the apex of the waveform for the explosion, this would be at the dark fiber on the top. and this is closest to the ski resort. Meanwhile, for the shoulder west, the shoulder center, and the shoulder east, they are all located at the landslide. And the most interesting of those is the shoulder center, because this really just contains or should contain events that come from the landslide. We can also look on the distribution of those signals over time and compare them with some independent data. So in this case, I compared it to precipitation. As expected, like earthquakes and common noise, they don't really have a correlation. But for example, the explosions, we can see they always happen when there's a strong precipitation events, but only in March and April when the ski resort is open and the precipitation comes as snow and not as rain. On the other hand, for example, for the shoulder west, we see quite a good correlation between the events and the precipitation. And also for the shoulder center, which we think are the most interesting events, there's a very weak correlation, but it's more delayed. But of course, this needs to be investigated in a bit more detail, also with source locations. So to conclude project 3, we developed an efficient method which can process 5 months of dust data quite fast. We used the sub-area analysis, and this allowed us to reduce time resolution, but also computational costs. And also we have improved sensitivity to small local events. For this data set, we detected over 7,000 events. And also to mention, we focused on very large events that happened on all sections. So if we would go lower for even smaller events, we would detect even more. And finally, the clustering revealed 6 metaclusters comprised of 30 subclusters. And again, this is quite nice. In the beginning, we have so many events. A lot of them are anthropogenic. It's a bit overwhelming, but after the clustering, we have quite a good separation of natural anthropogenic events, and we have clusters that we are interested in that we will can then focus on in more detail. So now I will conclude the main results of my thesis and give some perspectives. First of all, we developed and implemented efficient workflows to handle large-scale dust datasets. We demonstrated that coherence-based methods are useful for dust and can detect and characterize seismic events across diverse settings in urban areas, at volcanoes, and at landslides or slope instabilities. We did a very broad event detection using the covariance matrix analysis, but we can also detect weaker and recurring signals through template matching. And finally, we categorized events using unsupervised clustering. Actually, this works opens up quite a few possibilities of what we could do next. And as I already mentioned, like one of the most important next steps is localization with dust, because also this would help us incredibly with interpreting the clusters that we obtained. And right now, our collaborators in Zurich, they started working on this. So here's a small example from Cheered, who used the cable. And in the year before they took those 5-month measurements, they also had an active survey. So this is quite nice for testing. They have explosions with the true locations. And here's an example of the match field processing algorithm they used. And the result is quite promising. So this is a proof of concept. And the next step would be to apply this to those natural events that we detected. Then what I showed in the second project, the template matching is quite nice to extend subclusters and to study temporal evolution. We could also do this for the Coulomb slides. And finally, recently there has been many nice applications of supervised model for detection. But again, for this, we need a good training data set. And also we could use our final catalogs as an input for those supervised models. So I thank you all for your attention.